Before you train a machine learning model, there is something much more important than choosing the algorithm. You need to understand your data. In this episode, we are going to learn how professional ML engineers explore a dataset, find problems, discover patterns, and decide what needs to be done before training a model. This process is called Exploratory Data Analysis or EDA. Imagine someone gives you a dataset with 1 million rows and tells you, build a machine learning model from this. Would you immediately start training XGBoost, random forest, or a neural network? An experienced ML engineer wouldn't. They would first ask, what exactly is inside this data? EDA is basically the process of investigating your dataset before making important modeling decisions. We want to understand what the data contains, whether the data is reliable, what patterns exist, and what problems might affect our model. Think of EDA as a health checkup for your dataset. Think about visiting a doctor. A doctor doesn't prescribe a treatment just because you walked into the hospital. They ask questions, check your symptoms, and run tests. EDA plays a similar role in machine learning. Before treating the model with algorithms, we investigate the data. During EDA, we are trying to answer a whole set of questions. How many rows and columns do we have? What kind of variables are present? Are values missing? Are there duplicates or suspicious values? What does the distribution of each feature look like? And most importantly, what relationships exist between our features and the target? The first step is simply understanding the structure of the dataset. Imagine we are building a customer churn model. We might have features like age, income, city, and number of purchases. And our target could be churn. Churn is whether the customer leaves or stays. Each row generally represents one observation. In this example, one row represents one customer. Each column represents some piece of information about that customer. Understanding this sounds basic, but it's important because every later decision depends on knowing what each row and column actually represents. Next, we check the size of the dataset. Suppose we have 1 million rows and 25 columns. That sounds impressive, but dataset size alone doesn't tell us whether we have enough useful information. 1 million duplicate or irrelevant records are not necessarily better than 10,000 high quality records. Next, we identify the data types. Is a feature numerical, categorical, date, or a text, or is it something like an image? The type of data determines what kind of analysis and pre-processing we may need. Numerical features contain numbers. For example, age, income, temperature, transaction amount, or number of purchases. But even numerical variables can behave very differently. Income might range from thousands to millions, while age might only range from 18 to 80. EDA helps us understand these ranges. Categorical variables represent groups or categories. For example, city, subscription plan, device type, or payment method. During EDA, we want to know how many unique categories exist and how frequently each category appears. This can reveal problems such as extremely rare categories. For categorical variables, we should look at unique values and their frequencies. Suppose 95% of customers belong to just 3 cities, while hundreds of other cities appear only once or twice. That tells us something important about the distribution of our data and may influence how we pre-process the features. One of the first problems we look for is missing data. And we shouldn't simply say there are missing values. Let's delete those rows. First, we need to understand how much data is actually missing, which columns are affected, and why the values are missing. The reason behind missing data matters. Maybe customers simply don't provide their income. Maybe a particular system failed to capture income for a certain period. Or maybe people with certain characteristics are more likely to leave that field blank. These situations can have very different implications for our model. Next, we look for outliers. An outlier is a value that is unusually far from the rest of the observations. Imagine most customers are between 20 and 35 years old, but one record says 250. That's obviously suspicious. But here is the important part. An outlier is not automatically an error. Suppose you are looking at customer income and one customer has an income of 50 lakh rupees while most others are around 1 lakh. Is that wrong? Maybe. But maybe that customer really is a high income customer. So an ML engineer investigates the source before deciding what to do. One of the most important parts of EDA is understanding the distributions. A distribution tells us how values are spread across the dataset. Are most values concentrated around one range? Are they spread evenly? Are they heavily skewed? Are there multiple groups? For example, income is often right skewed. Most people may have relatively moderate incomes, while a small number of people have extremely high incomes. EDA allows us to see this visually. And depending on the algorithm and problem, we may decide to apply transformations such as a logarithmic transformation. A histogram is one of the simplest and most useful EDA visualization. It divides values into ranges and shows how many observations fall into each range. It can quickly reveal concentration, spread, skewness, and possible outliers. Another useful visualization is the box plot. It gives us information about the median, the spread of the data, and potential outliers. Box plots are particularly useful when comparing distributions across different groups. EDA isn't only about looking at individual columns. We also want to understand relationships between variables. For example, if we are predicting house prices, does house size have a relationship with price? A scatter plot can immediately help us investigate that. Correlation is another concept you will frequently see during EDA. It measures the strength and direction of a linear relationship between numerical variables. A positive correlation means that as one variable increases, the other tends to increase as well. But there is an important warning. Correlation does not mean causation. If two variables move together, it doesn't automatically mean that one causes the other. EDA helps us discover relationships, but we need domain knowledge and further analysis to understand why those relationships exist. We also want to study the relationship between each important feature and our target. If we are predicting house price, we might investigate house size versus price, location versus price, number of rooms versus price, and so on. This helps us understand which variables may contain useful predictive information. Don't forget to analyze the target itself. Suppose you are building a churn model and 90% of customers stay while only 10% leave. That's an imbalanced target. If you don't notice this during EDA, you might later interpret your model's performance incorrectly. Class imbalance becomes especially important in classification problems. Imagine a model that predicts customer will stay for everyone. It would already achieve 90% accuracy in this example. But the model is completely useless for identifying customers who are actually going to leave. EDA also helps us identify duplicate records. Duplicates can happen because of data ingestion problems, repeated transactions, or system errors. But again, we shouldn't blindly delete duplicates. First, understand what the duplicate actually represents. EDA can also reveal values that technically exist but don't make sense. An age of -5, an age of 250, or the same category represented using different formats. These issues can silently create problems in a machine learning pipeline. One of the most dangerous problems EDA can help us detect is data leakage. Data leakage happens when information that would not actually be available at prediction time somehow enters the training process. The model then appears extremely accurate during evaluation but performs poorly in the real world. Imagine we are predicting on January 1. whether a customer will churn. But one of our features contains their cancellation date from January 15. That's information from the future. The model can essentially see the answer. This is why an ML engineer must think carefully about when every feature becomes available. This brings us to an important concept, time. In many real world machine learning systems, data changes over time. We need to ask, when was this data generated? Was this information available at prediction time? And does our training data actually represent the environment in which the model will operate? One common misconception is that EDA simply means creating charts. It doesn't. EDA combines statistics, visualization, investigation, and domain knowledge. A graph can show you that something is unusual, but understanding why it's unusual often requires you to investigate the source of the data. In Python, libraries such as pandas make the initial EDA process very convenient. For example, we can inspect the shape of the dataset, understand data types, generate descriptive statistics, check missing values, and count duplicate records. These are simple commands, but they are part of everyday workflow of an ML engineer. For visualization, Python engineers commonly use libraries such as matplotlib, seaborn, and plotly. The goal isn't to create beautiful charts just for presentation. The goal is to use visualization to discover patterns, anomalies, and relationships that may not be obvious from raw numbers. So, if you want a simple mental framework for EDA, think of it as a sequence. First, understand the structure, then inspect data types and missing values, analyze distributions and outliers, study relationships between features, understand the target, and finally look for issues such as leakage and data quality problems. This is one of the biggest mindset changes I want you to take away from this episode. A beginner often starts with, should I use random forest or XGBoost? An experienced ML engineer first asks, what does my data look like? Because choosing the algorithm before understanding the data can lead you in the wrong direction. Before moving toward model training, you should be comfortable answering all of these questions. How big is my data set? What type of variables do I have? What is missing? What looks unusual? What relationships exist? Is the target balanced? And most importantly, is there anything here that could make my evaluation unrealistic? EDA is only one part of the larger machine learning engineering workflow. We start with data, we explore and understand it, we clean and transform it, we engineer useful features, then we train and evaluate our model, and eventually we take that model into production. If you remember only 5 things from this episode, remember these. First, understand your data before modeling. Second, use visualization to discover patterns. Third, investigate unusual values instead of automatically deleting them. Fourth, always watch for data leakage. And fifth, understand your target before deciding how to evaluate your model. A machine learning engineer isn't someone who simply knows dozens of algorithms. It's someone who can take messy real world data, understand what is happening inside it, identify problems, make good engineering decisions, and then build a reliable system. And EDA is one of the first skills that helps you do exactly that. In next episode, we will go one step further. We have discovered problems in our data. Now, what do we actually do about them? We will learn data pre-processing and cleaning, including missing values, categorical encoding, feature scaling, and how to build a proper pre-processing pipeline. That's where we will start turning raw data into data that a machine learning model can actually use. See you in next video. Thank you for watching.